Let's see, sir, how many participants are there?
Yeah, around 190, sir. Maybe
190.
200 now. Not me.
Yeah, yeah. Yes, so let me share the screen. One minute, sir. I'm trying to open that file which I created. Yeah. Okay, so a very good afternoon to all the participants once again. So again, Pillai sir nicely briefed about the plants. So in today's session, we'll touch about quantum materials. Okay, right? So yeah, so this is only a 2-hour session, very short session, right? So during this session, how much we can cover, that much we will try to do it. Okay, right? So basically, there is a full-fledged course on quantum materials as a QT-08. Okay, so as in the case of introductory QT-01 or 00 and 01, so the quantum materials were put as a one of the small module to give a flavor for you people to get into that. Okay, right? So if you go and see the syllabus there, the introduction to quantum materials, okay, so you have band theory of basics, correlated systems, magnetism, superconductivity, 2D materials like graphene, okay, and topological phases of the matter, okay, and some survey of material growth techniques. How is this materials were grown or prepared? So that is the entire, like say about 20-hour to 40-hour lecture series for quantum materials as a QT-08. But for this particular QT-00 and 01, you would be getting some intro to that, the full-fledged course. Okay, right? So before going there, let me see. There are 233. So I have made some PPT here. I have made a PPT, and also I have my hand notes, supporting hand notes for discussing about some basic fundamental physics required as a part of quantum materials. So what I'll do, I'll go through the PPT first, and then we'll in the second half, and once we finish with this PPT, we'll go to that the required handouts. Okay, so fine, let me go to the next slide. Okay, here you see, why do you need to study quantum materials? Actually, you are committed for quantum computing, okay, but why do you need a quantum materials? That's the question. Okay, so yeah, so here if you see, there are very important 4 reasons are there why to study. Number one, quantum materials are the physical foundation of quantum computing systems. whatever quantum computing we are doing as of now, okay, the qubits are involved. The qubits were prepared out of this quantum materials. Okay, so the quantum computing is based on quantum physics laws, which means the hardware which we need is made up of the qubits, or the quantum qubits are very small in size. So those are behave as per the laws of quantum physics. So we should better know what is this quantum materials being used to realize the qubits in various ways. Okay, that is the foundation. Okay, the next point is understanding their properties is crucial for building scalable quantum computers. What I mean is, let's say I have one qubit, I have one more qubit. Okay, how when I bring them together, how they interact? Let's say there is a photonic qubit is there, that is called a flying qubit. There is a static qubit, electron as a qubit is there. Let's say it's a spin up, a spin down. How when I bring them together, the electron should transfer its qubit information to the electron, or electron can transfer the information to the flying qubit. As it goes through the electron, it should have the information of that electron as it travels away from it. So there is an information transfer should happen, which means there should be interaction between this flying qubit and static qubit. Okay. And by the way, if I don't know how they interact, I can't design my qubits interaction. I can't design some kind of a quantum operations. I can't design a quantum circuits. So I better know how they interact. That is possible by knowing their properties. How they interact is actually dictated by their properties. The moment I know how to do that, how to understand, okay, what I can do, I can plan a vast network of qubits where lot of amount of data could be uh, processed. Okay, right? So that is what the quantum materials, we should know what they are and how they behave, their properties also we should know, so that we can scale a quantum computation for a large amount of qubits. Okay. The next question is, sorry, next reason is they enable the manipulation of control of quantum states. Okay, right? Fine. So they enable the manipulation. So these quantum materials enable the manipulation of control of quantum states. Means, let's say I have a quantum gate, sorry, quantum states are there, or qubits are there. I want to change them, process them through some gates. Okay. So how these gates were realized in the first place? Sometimes for using the pulse of photons, I realize the gates. Okay, so the pulse of photon is not a material, but it's a quantum, a qubit, flying qubit. So I should know how to control these quantum states. So if I know how to control, then I can go for quantum computing. Okay, and the last reason is research in the field drives the technological breakthroughs and innovation. So the research, if you go in-depth further research in quantum materials, if you do that and if you understand them, then you can come up with the new materials and you can come up with new quantum hardware. In that way, you can understand the quantum computing in a better manner, and also you can do the quantum computing in a better manner. Okay, right? So that's the main four reasons why we need to study quantum computing, sorry, quantum materials. Okay, right? So let me go to the next slide. On the right, I have a nice diagrammatic interpretation of these four reasons. There it says quantum materials are the foundation or physical foundation for quantum computing systems. Why? Because they are the foundation of quantum computing, and they allow this. Knowing them, we can scale quantum computers, we can manipulate the existing quantum states, and we can do breakthroughs in technology and innovations of quantum computing if you study quantum materials. Okay, right? So let me go to the next slide. Okay, so again a colorful slide I have here. Okay, what you see is, what are these quantum materials? Okay, right? We are all the way talking about quantum materials. We should study them, right? So first of all, what is the question? What are they? Okay, the number one is, okay. Let me log in with another system so that I can see directly to the camera. Okay, give me a minute. Just a minute. Meanwhile, if we can see what I have in my slides. Okay, right. Yes. Okay. Right. So here, if you see in this slide, you see that there is a definition of quantum materials. Okay, what it says is materials that exhibit the quantum mechanical properties at macroscopic scales, including, there are so many things. Okay, it's very interesting. The statement is very interesting. The quantum materials, see, quantum particles are the ones which are so tiny. Individually, they show quantum behavior and they behave as per the laws of quantum physics. When you combine them, they are microscopic, very, very tiny. If you combine them, put them all together, what happens? They become macroscopic, large. I'm not saying very large as our classical word. They become, compared to very tiny single atomic, to a large number of qubits they will become. Okay, so if they become like that, now the question is, what kind of a physics laws they will behave, like they will satisfy, or they behave as per the which physics laws? Of course they still behave as per the laws of quantum physics, because they are not as large as our classical objects like a mobile or anything. They still, when I combine them together, if you see them, they're still very, very small. Okay, so they behave as per the laws of quantum mechanics. Okay, and they show the properties accordingly. So what are these materials? Let me write list down few. Okay, on the right you have figures one by one. I'll show you what are those things. Okay, so I can point out. I can point out here. Let me see on the PDF. Is there a, yeah? Okay, right. So I can do something here. Okay, fine. If you can see now on the list, you have superconductors. Superconductors are the materials which have zero electrical resistance. Okay, for example, if I take a wire, it's consisting of electrons which are moving from one place to other place through the wire, but along the way they hit with the new other nuclei, they hit with other electron. So what happens? They are going to have a resistance for a smooth travel. Okay, because of that, there is a very less chance that they move freely. So because of that, there is a collision, there is a heating up may happen. So the conductivity of energy through the electron may not be as free uh, as as we think. So there is a resistance created. Okay, but I have a material They are some kind of a conductors. If you reduce the temperature of these materials to certain critical temperature, okay, after that point what happens, this materials becomes a zero resistance, means as if there is only one electron is there, he is traveling very smoothly in the electron in the conduction corridor, okay, or there are electrons as if they move in a straight lines without eating each other. So absolutely zero resistance. How it is possible? Because it's consisting of so much materials, but how come they travel with much ease? Okay, and they travel with much ease, and also they do a lot of work, just like electrons being put together and forming a pair. So that is what shown on the right side here. Usually, electrons possess a spin up or a spin down. Okay, right, just like our earth, if we just take a electron, okay, right, if we just take an electron, what happens, the electron rotates about itself in clockwise or anti-clockwise. If it rotates about itself, what happens, it creates a I'm sorry, it creates a magnetic moment along its axis that is going to be shown as a spin up and spin down, okay, right. So usually a spin up, yesterday we saw magnetic moment of an electron is a small bar magnet which is just like a north and south pole. So if I just bring two north and south pole, two magnets in an opposite way, they will attract each other, okay, so they attract each other. Then what happens, two, I can bring two opposite spin electrons put together, okay. So basically what is happening inside a lattice, means a collection of atoms, okay, there are all the atoms are arranged in that, there are outermost electrons, valency electrons, which are coming out of the atom. Those electrons we will take, if that spin are the electrons which are still existing in a valency orbit, in a single valency orbit I can't put two electrons, okay, okay, if their spin is same we can't put them, the spin is opposite we can put them, okay. So that I somehow, even outside the atom, I can pair the electron by bringing that spin into consideration. So there is something called a Cooper pairs are formed. So these paired electrons become so powerful, they travel with much ease and much fast, okay. So that is the main key factor in the case of superconductors, which is shown here at the right side, okay. Now there is something called a topological insulators, another kind of a quantum materials which could be used to realize, a qubits out of it, okay. So what are these topological insulators is, let me use a different color, okay, right. So the topological insulators, the figure is given at the right top, okay. So what are these things is, they take a very fine thin film, atomic film, in in on the film there exactly one electron exists, okay. If you take, by the way, this is a very thin film, and moreover this thin film is, okay, right. So this thin film is, okay, it's consisting of, okay, let me write down quantum materials, okay, we are talking about topological insulators, okay. So very thin film of insulator, if you just take, so insulators by nature what they are is, they are There are atoms where the outermost electrons were strictly held. Okay, strictly held to the atom, so electrons are not coming out. So if there are electrons, they are stuck to the nucleus, stuck to the atom. So if insulators are there, if I have insulators, let's say there is a nucleus, electrons are around the nucleus, they're just revolving on their own, they're not able to come out of the atom. Now, okay, what happens if I send a magnetic field through this film? Very strong magnetic field. Okay, so magnetic field comes out. Okay, because of that, what happens? This magnetic field induces lot of magnet, there is a force, right? Lorentz force, magnetic force, Q multiplied by V cross B is the Lorentz force for a moving charge. If a charge is Q, if it is velocity is V, if it is moving perpendicular to the magnetic field, okay, in that case, there is a force acts on this particular moving charge. So if I just take the, the charge, the magnetic field is along the direction of the middle finger, and the index finger shows the moment of the electron, and there is a force which would be generated perpendicular to that V cross B. So that force would be perpendicular to V cross B. Let's say if the V and V is on the plane, B is perpendicular to the plane, and the N would be just on the plane itself, it will be there. It will move the electron away from the nucleus. For example, here electron is there, the force will move the electron away from the atom. So what happens? All the electrons at the boundary come to, so the atoms, okay, electrons would go to the boundary. So those electrons would start traveling and start contributing to the current at the edge, not inside. Inside, what happens? Electrons are revolving. So they are not going to contribute any current on the surface, but at the edge, there is some current which is actually created because okay, because of the electrons which were knocked out, they're knocked out to the boundary because of this Lorentz force. Okay, so by the way, the topological insulator should not allow the electron to go out, but the boundary electron, see this electron would contribute some current, this electron would contribute some current. Okay, there is a one atom, one nucleus, and the electron contributes some current, some contribute. So individually they add up, and the current would be created, electron current, okay, only in the boundary. Okay, but why not inside? If you see inside, there is a current due to this electron in this way, there is a current due to this electron in the opposite way. They'll just nullify the current completely. So there is a no contribution comes from the such insulator. Okay, right? So topological insulators would contribute to the current. Okay, they constitute, you can say, they constitute the current at the boundary. Okay, so that is a current, by the way. So that is a very good. And one more issue with this is, okay, and this current may not be always in a clockwise or anti-clockwise direction. It can be both. Okay, so that is, let's say, clockwise is a one way of saying quantum state, anti-clockwise another way of saying quantum state. This is like a 0 and 1 kit. So at a given point, since it's quantum in nature, I see the chances of current being in both the directions. right? So I'll have a quantum qubit state from one of the topological insulator. Okay, so alpha 0 plus beta 1. Fine. So this is the topological insulators being showing the quantum qubits. Okay. The semiconductor qubits we just earlier we saw, sorry, superconductor qubits earlier we saw, where the inside a material, when the temperature goes up like below critical temperature. Okay, let me write this current direction. Okay, current clock. Okay, this is anti-clock, na? Anti-clock, and this is the current clockwise. Okay, right. So the superconducting materials, what happens? The current becomes without any resistance when you reduce to absolute zero temperature, 0 Kelvin temperature. Okay, it's very cool. Now let's get back to our PPT. Here, if you just see, the first one is superconductors, second one is topological insulators, the third one is called quantum dots. Okay, what I mean by quantum dots is, right, that if there is any means I can take some charges, let's say electrons, all of them in a three-dimensional space, if I confine spatially, they are going to execute different kind of quantum states. So that is a very good means for realizing a qubit. So it's a three-dimensional confinement of the electrons. So here I have showed you the quantum dots of semiconductor based quantum dots are shown. Here they are very small nanostructures with discrete energy levels. They exist at discrete energy levels. In fact, what they are is, inside a semiconductor crystal, we can confine the electron to some location. In that way, we can realize a quantum dots. Okay, and these quantum dots would exist with a different energies. So those energies, I can pick a couple of energies from them. Okay, so there's so many energies. Let's say there is N1, N2, and N3 energy levels. So let's say I pick two of the energy levels and realize qubits out of it. So that is what quantum dot based quantum materials are, quantum dot based quantum qubits. Okay, right? And there is one more thing, two-dimensional materials, graphene, okay, transition metal, chalcogenides, okay, right? So that you just take a graphene, just to take a graphene. Okay, it's like carbon arranged in very packed manner. So this has the beautiful properties. Earlier, like 10 years back, so for every experiment graphene was added to enhance the results or to enhance some properties. So even for quantum computing, graphene could play a very vital role. So this behavior comes from the graphene because we were able to put the graphene at a very thin single atomic level or layer level. Okay, that's why people should study the graphene or 2D materials which are made up of only carbon. Okay, right. So the next one is something called spin liquids. Okay, basically it's like a collection of many spins. They can show the dynamical properties of the liquid, something like a flowing. Okay, so these are exotic magnetic states with the quantum entanglement. Okay, right? So this is just like one figure I just showed you to, okay, exotic materials, right? Okay, so that was here. Okay, so something like with some material which is having spin particles with a spin or some magnetic moment. If I bring a large magnet, they should flow as per the magnetic field exerted by external bar magnet. In this case I have a hook magnet. So there you see the part, like magnetic particles are aligned as per the momentum, sorry, the magnetic field lines of this hook magnet. Okay, so these are the very basic quantum materials which show the quantum physics properties even at a macroscopic level. You see, I'm not talking at a single atomic level or single electronic level. I'm putting all of them together. Even then, they are behaving as per the quantum physics laws. Okay, right? So let me go to the next slide. Okay, yeah. Now, the next slide shows the historical research breakthrough in quantum materials. What was happened so far? Okay, what was happened so far is it all started in 1980s. There is something called quantum Hall physics. Okay, quantum topology was studied. So, if you all heard about quantum Hall effect, where okay, if there is a material is there, if it is exposed to the magnetic field, okay, right, if there is a current flows through, okay, what I mean, let me explain with my hand notes. Okay, quantum Hall effect, quantum Hall effect. Suppose if I have a material, if I connect this side to positive plate, okay, right, one side to positive plate, other side to negative plate. This is positive, this is negative. Okay, so the current would flow in this way, right? I would flow in this way, means the electrons are flowing in this way. Okay, now if I apply a magnetic field perpendicular to this particular the slab, let's say there is a slab of current carrying, what happens, the charges again because of the q into v cross b, that Lorentz force, because of Lorentz force, charges start accumulating on the edges of this material. Okay, so where it will accumulate, so now let's say the current is perpendicular, the current is shown by the index finger, magnetic field is shown by middle finger, so the current is moving, okay, from left to right, magnetic field is the top, so the positive charges will be moved top, okay, right, and negative charges moves towards the down. So now it is just like a positive plate at the top, like a capacitor, and negative plate at the bottom. So there is an electric field maintained, a potential difference is maintained, V is defined, maintained between these plates, and they act like a capacitor. Capacitor. Okay. Q is equal to CV. Okay. Q is equal to CV. So how much capacitance, how much charge is accumulated? Depending on the voltage. Right? V is equal to Q by C, where C is the capacitance. Right? So what happens? This is actually Hall effect. This is known after Hall. So this was back then like perceived or invented. Okay, so it all started there. Quantum topology. Topology means it's a mathematical concept. Okay, so it only worries about the shape or the property of the material, right? And this property of the material, it is not going to change even when you dislodge. What I mean is, okay, topology, let me understand, let me view what is topology. Topology is, let's say I have a donut, it has a hole, okay, with the hole. Now let's say I have a cup, okay, cup has a handle, and a cup has a handle with a hole. Okay, now you see the both are equivalent equivalent as per the topology. What is that is, both have holes. Okay, if you dislodge the cup into a shape like a donut, you can just dislodge the cup into donut like that. Okay, and still they are said. So mathematically, they are having single hole. That is what the topology says. So that is what quantum topology. The quantum materials, their properties are not going to change even when you dislodge or discharge their structure. So the property remains the same. That kind of a material actually called a topological material. Topological material. So in fact, the topological insulators are of that kind. Okay, whatever we discussed just now, they are of that kind. They are not going to be behave differently when you deform the structure of this material. So it still show the same quantum behavior. Okay, so that means they are very rigid. They are rigid for the environment. So they are very good means to realize very steady quantum qubits. Okay, fine. So let me go back to the PPT. So that is what the actual quantum topology study was started in 1980, and which is in fact led to the Hall effect. Okay, and then the superconductive age was also started. So where things become absolutely zero resistance below certain temperature, threshold temperature or a critical temperature TC. So that was 1980s research. 1990, okay, topological berry phase. Okay, so upgradation. We are not getting to the detail. So new particles and fractionalization was done inside the particle. What is there inside? Those things for people studied, and then people started even studying nanoscale physics. Okay, right? So they are going at a level of 10 to the power of minus 9 meters. Okay, so at that level, what are the behavior of the particles? People started studying in 1990s with the advancement in the technology. Okay, and as of now, topological insulators and spintronics, multiferroics. The ferroics are the iron, ferromagnetic materials are there. Na? So those things involve multiferroics are those things. So as of now, people are exploring these materials to have all a better qubits or any other better application. And cold atoms and advanced spectroscopy, quantum simulator, and nano devices were also being explored as of now. Okay. So devices using quantum materials is the key to have a quantum computer, which were being explored right now. Now, what could be the future with the existing knowledge of research? So, what could be the future is we can use quantum computation with these materials and do quantum cryptography or secure communication. We can realize. So, we can come up with the quantum repeaters. We can launch at different node points, just like amplifiers, which we are doing right now for a classical communication. In the same way, we can have quantum repeaters realized out of quantum materials. Okay, and the next thing for future is topological electronics. As of now, all the electronic chips which we are having, they're like silicon based, p-n junction based transistors made up of this p and n junction. So in future we may have electronics based on topological insulators. Okay, so that may be the future, because they may lead us to have qubits and lead us to have a better computing. Okay. The next one is above room temperature, superconductivity and mentronics. That's a very interesting thing. So but then in like a couple of years back, I think ISC, there is a research team which claimed that they have a superconductivity seen at room temperature, which was still debatable. There were some contradictions. You keep those aside, but if you can realize superconductivity at a very, very room temperature, the real ambient temperature, what happens? We can still realize quantum qubits without any cryogenics, without any cooling, and it becomes very easy to realize. Our real hardware you can put together without any refrigeration units. Okay, that means everybody can have a quantum computer in their offices. Okay, without having any need for cooling. Okay, so this is the survey of the research. Okay, with respect to quantum materials. Okay, let me go to the okay next slide. Okay, are we going? Yes, are we going in a right way? Yeah, right. So the next one is the critical research areas being explored. So if you see here, as of now, the qubits, if you take, they're prone for the they are actually fragile and they are prone for external disturbances. Okay, because of that, what happens? The coherence of the qubits were disturbed and they become decoherence. So one has to understand how these quantum states could be preserved inside the materials. That is very important. So that is one of the critical research. Not only just come up with the error correction, so you have to attack the root cause of this decoherence. So that only possible if you have a better understanding of this quantum material, how they work. Okay, and while working you should also find out where exactly the noise is coming from, how the errors are occurring inside this material, how this qubit state is supposed to be behaving a nice quantum state are not behaving as per a normal quantum state, having some noise. So we need to identify that, and we need to develop materials with a longer coherence time, right? So the T1, T2, which we have, yesterday we discussed, the T1 corresponding to the lifetime of the electron existing in the excited state. T2 is the lifetime of superposition to exist for a given quantum state or a quantum superposition state. So this T1, T2 must be having a very large amount, large number, so that I can have more computations could be more computations we can do on a given qubit. Okay, so longer coherence times means the longer t1 and t2 times. Okay, for a qubit. Okay, and the quantum error correction materials that support topological protection and fault tolerant quantum computation platforms, reducing physical error rates. Okay, so the FERC coming up with better quantum error correction, one can come up with a material based correction. What is a material based correction? One thing could be you realize qubits out of topological materials. So in that way, the topology protects the system from the external deformation because of the external involvement. Okay, so in that way we can have the root cause are addressed. At the same time, the root cause is not going to affect at all because of the material topology. Okay, rigidness. Okay, so the fault tolerant quantum computation platforms are possible with these things. Okay, and we can reduce the physical error rates. Okay, so errors comes from the physicality of the system. Those things can also be addressed. And right now the critical research one could look for is also on the scale challenges. Okay, so to bring multiple qubits together, let's say qubit 1, qubit 2 connected, qubit 3 connected, qubit 4 connected. You see, this is now qubit 1 and qubit 4 are not connected. Qubit 3 and qubit 2 are not connected. Okay, Okay. So what? Yeah. What should I do here is materials for interconnecting multiple qubits we have to come up with. Okay. So the material should support that kind of interconnection and maintaining quantum properties at larger scales. So like if you separate and put a large number of qubits, so there should not be any like some qubits at the end should not go without behaving like a qubits because of they are very far from the addressing point. Okay, so that is one of the critical research one can look in the case of quantum materials. So integration with the classical electronics, this is also important thing. So your qubit network not just only work with itself and give some result. The result has to be analyzed or transmitted to the classical analyzer or classical computer. So a classical electronic should be able to connect to them. Let's say some detector, some information coming from the qubit in the form of flying qubits, the light. So the light has to be observed by a detector. So the detector should be of appropriate interconnection. Okay, right? So there is a suitability there. Fine. Okay, that's a photon or any radiation by you mean. Okay, so these are the critical researches one could look for in the quantum materials. Okay. Now, what is being currently explored for realizing qubits? The current quantum computing platforms. Okay, so the number one current platform is superconducting qubits. These are actually called transmons. This is called transmons. Okay, so that's simple LCR circuits, by the way. Only thing is in place of inductor. So LCR circuit is what? LCR circuit is there is an inductor, there is a resistor, there is a capacitor which is connected to a battery. This is a LRC, LCR circuit. Okay, so this is a oscillator, by the way. Remember what is oscillating? The capacitance charging oscillates between certain two values. Let's say capacitor charges between 0 coulomb to 20 coulomb. Sometimes it goes to 20 coulomb and then discharges. And then the charges. Let's say it charges between 10 to 20 coulomb. Okay. And if I have a oscillatory battery, okay, oscillatory battery if I have, instead of the like a static battery, if I have a oscillatory battery, okay, so what happens in that case? The capacitor charges between certain number of charge states, let's say 5 coulomb, 10 coulomb, 15 coulomb and 20 coulomb, like that. Okay, but like if I just, this is a quantum states, I can realize a qubit out of it. Okay, this qubit, if I have a charge states like 5 coulomb, 10 coulomb, 15 coulomb, and 20 coulomb. If I try to realize a qubit out of two states, there is always chance that qubit information lost to other two states because they're also equally spaced by distance, by energy, by charge. So to just to mismatch the energy separation or charge separation, what people thought is they replace the inductor with a Josephson junction. What is Josephson junction is? There is a superconductor, there is a superconductor insulator. Okay, so let me use my hand notes. Okay, so transmons are a simple Josephson junction, superconductor, insulator, superconductor, and the capacitor. Okay, so let me draw both in parallel. Yeah, I think it is fine. ELC. Okay, let me undo. Where is the undo? Somewhere? Yeah, here. Okay, so let's have a capacitor. Let's say now I'll connect with the oscillatory field. Okay, now what happens? Interestingly, the capacitor charges between, let's say, 5 coulomb, 10 coulomb, next 13 coulomb, next 14 coulomb, next 14.5 coulomb. Like you see now, the energy separation or charge separation are unequal. This is 5, this is 3, this is 1, and this is zero point 0.5. So if I realize a qubit out of two states, okay, if I realize a qubit out of two states, the information is just real, like contained or confined qubit information, qubit confined to 5 coulomb and 10 coulomb states. Okay, that is a very good thing, na? So that is what Josephson junction is doing. And why it is Josephson junction is doing? Because in the superconducting material, okay, superconducting electrons pair up, like opposite spin electrons pairing up. So this is called Cooper pairs. So these Cooper pairs, this is insulator, this is superconductor. So these travel into the other side, and when they are not going to keep quiet, they come back and they make a oscillation between left to right with some frequencies. Let's say frequency 1, frequency 2, and so on. They oscillate with multiple frequencies. These frequencies adds up to the capacitor and creates some kind of a voltage oscillations in such a way the capacitance exists in multiple states like 5 coulomb, 10 coulomb, and 3 coulomb. Somehow I confine the superconductor to have only one frequency. In that way, I can realize only qubit between 5 coulomb to 10 coulomb. Okay, so this is just equivalent to naturally occurring atom. That's why the transforms are called artificial atoms. Okay, they're called artificial atoms, right? If you just take natural atoms, nucleus is there, first ground state, second ground excited state, and third and the fourth, like that. They're very, very close. As you go further, the orbits are very, very close. This is large, this is small, this is much small, and this is much small. Okay, so non-linear energy barrier or energy separation. Okay, let me write separation. Okay, fine. So let me get back. So those are the transmons. And now one more qubit realization platform is trapped ions. Ions can be trapped. Okay. So there is some more points I have here on the slide. The materials used for superconducting qubits is aluminum, niobium based circuits. Okay. And for advantages here is superconducting qubits advantages is fast gate operations. You can mature fabrication. Okay, right? Much more better fabrication. And challenges is again short coherence lifetime and refrigeration requirement because superconducting materials are involved here. Okay, and in the trapped ions are trapped between the electrodes, and to talk to them, to communicate with them, there is a lasers are used. Okay, so as if we pick something with a tweezer, okay, we pick something and put it somewhere. In the same fashion, we can trap the ions between the electrodes and work with them. Okay, so that is the trapped ions. And what are the advantages with trapped ions in the laser system based qubits? Okay, high fidelity operations and long coherence time. So let me get back. What is the fidelity? Fidelity means, I think it is being discussed already, I hope. But anyway, I'll have a, let's say I have a qubit, let's say Q1. I put the information, let's say this atomic based or artificial atomic based qubit. Okay. So there is a quantum state I want to store. Okay. I just store a quantum state inside that. Let's say alpha 0 plus beta 1. I'll just store. Okay, so let's say when I say one information, I have many such things, many qubits. Okay, many atoms, they will just store that information at a time. But the thing is, I can't store them perfectly. There are atoms which, let's say, there is one qubit with 60-40%, which is what I want, but there is a one with 61% to 39% excited and ground. Excited and ground. In this case, what happens? I have a probability of the collection of all the atoms exist in quantum state 1, quantum state 2, and so on, some quantum state n. So there are so many combinations that slightly vary from each other. So in that case, I can't simply write with the one quantum state equation. There people write in terms of something called density matrix. Okay. What is density matrix is, take the quantum state outer product, which is going to give you a matrix. If the quantum state here is 2 by 2, so you'll get, so 1 by 2 dimension, so I'll get 2 by 2 dimension density matrix. Okay. In this case, I'll have alpha square, beta square, alpha beta star, beta star. This is the quantum state I'm going to get. Okay. Right. So now, if the quantum state is in a pure form, I'll have that. But I have a mixed system, right? It's a mixed state. So in this case, now I have to write a total density matrix as, there is a chance with the probability P1, there is a quantum state. Any given atom can exist, or a qubit can exist in row 1 style, or row 2, and so row n. So this is the overall density matrix. Now coming back to the fidelity. What is fidelity is, I intend to store the information psi into a quantum hardware, into a quantum memory. Okay, right? Task is to store psi into quantum memory. Now the quantum memory is stored, but when it is retrieved, okay, it gives me a psi prime, not exactly the psi. Now the question is, how close? The question is, how close psi and psi prime are? Question. If they are close by 99%, so we say if 99% close implies the fidelity is 99%. I need that. Otherwise, my information, if I store some information, I give something else, I'm not satisfied with that. So the fidelity is a very, very important key. So here the trapped ion based qubits are high fidelity and they have a very long coherence time, that is T1 and T2. So I can realize more operations on them. Okay, they have their own pluses and minus, and realizing the structure is not that easy because it's all the related requires a hardware. Okay, fine. And the semiconductor qubits just now I talked about is silicon and gallium arsenide quantum dots. You take inside the semiconductor material, you trap the electrons to a three-dimensional location, which is going to realize, like create some kind of a quantum states. What kind of a quantum state it's going to come up with? A spatial quantum states. Let's say there is a state of location 1, there is a state of location 2 and so on. So with the two locations, I realize a qubit. Okay, so that is what the quantum states are, and this one exists with some energy E1, this one exists with some energy 2 E2. Okay, so this is how quantum dots can allow us to do quantum computing. So advantage here is compatibility with existing technology, because existing technology is purely based on p-n junctions. Okay, p-type material, n-type material, and so on. And the challenges is it is sensitive to the environment, because you are actually confining the collection of electrons into a particular location, and there is always chance that some nearby source host atoms inside a semiconductor or a dope can just grab this electron and consume this electron. So that is the problem. So the environmental sensitivity is there in this semiconductor materials. Okay, right? So let me go to the next slide. Emerging material platforms. Okay, so we will have a quick break for 5 minutes, and then we will come to this point. Let me see any chat questions. No questions. We are having a 5 minute break, everyone. Just have a sip of water, tea, or something. We'll restart at 4:08.
Yeah, participants, we are having a break time now. So you can meanwhile type any questions if you have. Once sir comes back, he will answer. There will be one more quiz which will be announced. So please be ready to complete the quiz. Tomorrow we'll be having one lecture that will be by Professor Anil Prabhakar, who is the quantum hub person from IIT Madras. So it's a privilege that he will be there with us. So please do not miss tomorrow's lecture. And after that, we'll have the valedictory session for QT-0001. Tomorrow will be the last date to pay the fee, right? We will send an email also. All those participants who want to get a certificate, only those who have paid the fee by tomorrow. We don't need money. So please don't worry. You can attend the lectures free, no problem. You can write the quiz also, no problem. But certificate will be issued only for those who have paid the fees, right? So please, after tomorrow, I cannot permit anybody. So please try to understand that this is something which you have to manage, right? Please complete the registration process by tomorrow. After that, we will not be able to encourage anybody. QT-002 onwards, again, we will open the registration process. QT-0001 registration will be closed tomorrow. Only those who have paid the registration fee will be issued the certificate. Certificates will be issued shortly. And we are also getting permission from National Quantum Mission, hopefully. So if that also comes through, then we will have the logo of National Quantum Mission, and of course, all these things that will be there. So the wonderful certificate will be created for you. So please look forward. So I request all of you to complete the payment of the fees without much delay. And those who are not doing any, who have missed the quiz or something, if you want to attend, please let us know. Please drop an email to fdp.academy@mnit.ac.in, which you all know. So please send the request and we will try to do it shortly. Right? We will resume in about 1 or 2 minutes after sir is ready. Okay, sir. Ashwath, sir, if you would like to
Yeah,
start.
yeah, I can
Right, sir.
start. Yeah.
Thank you.
Okay then. So we'll restart. Okay, fine. So emerging material platforms for the quantum qubits. Okay, as of now, right? As of now, these three platforms were being used. The current platforms. One is transmon and ion traps. Okay, other one is quantum dots. Okay, right? The upcoming the qubits for the quantum hardware could be the topological based quantum qubits. We just discussed earlier the topological based quantum qubits, what they are. Here specifically they have given Majorana fermions. Okay, so I think Microsoft earlier claimed that they have some Majorana based fermion based the quantum chip, which is what like it's capable of working much faster and much beyond what is the existing computation. There was a claim. So the other corporations, Google and all, they objected it. So there is no much debate going on. But the what one can say is Majorana fermion based quantum qubits are going to be very, very effective quantum qubits. Okay, so Majorana fermions in superconductor semiconductor hybrids is another thing people can think of with the emerging technology. And what is the promise? Inherent protection against certain types of errors. Okay, some errors are there which can be easily addressed. Okay, and it is has a barrier, like some kind of a barrier where the errors cannot cross. Sir, okay, there is a question people are asking here. Can we work with multiple platforms in quantum computation, that is hybrid platform system? So that Dr. Rajeshwari ji, so that is what topological qubits could be a hybrid ones people can think. And people are already started working with photonic based and material based combination, the hybrid quantum computers. Okay, right? Yes, of course, it's possible. Only question is how well they both integrate with each other. How well you can connect this one type of a qubit platform with another qubit platform, make them interact and evolve as a whole together. That is a challenge. Okay. And one more question by Srinivas Ji. Sir, I may be asking an odd question. Is there any possibility for having quantum states established in human system? For example, saints experiencing the Samiti state. Okay, very, very interesting and fun question here, Srinivasji. Okay, let me tell you one thing first. There is nothing like a odd question or a bad question in quantum physics or quantum mechanics. Every question is a potential a question which leads to very good discussion and research. Okay, so your question is absolutely fine. Okay, what you are asking me is there a way quantum behavior could be seen at the level of we humans? Okay, the question. Let me write down the question. Any possibility to see the quantum behavior at classical level, classical, or I can say macroscopic level. Okay, our level, our size. The answer to this question is right. Yeah, the saints would back then they go to samadhi state, na. So there they are actually in between. They are in between the life state and also dead state. Okay, their entire tissue and everything, every cells will go to a, let's say, a stable state. No need to have any energy. They are just staying, waiting for to be awakened. Okay, and that state we can't certainly say it is dead or alive, it is existing in between. So that is what we can think methodologically, just like a cat inside a Schrodinger cat inside a Schrodinger cat experiment. Okay, so there Schrodinger cat experiment, if you see, the cat is dead or alive, it is in superposition because there is a poison. Okay, there is a cat. Okay, cat is there, there is a poison. Okay, there is a poison in a container, poison. Okay, there is a hammer. Okay, hammer, this hammer will hit the container, spill the poison. Okay, if it spill the poison, then cat is dead. The hammer hitting or not is in superposition of some radioactive material. Okay, what is this is, there is a radioactive material, it can radiate or it may not radiate. So when it radiates, it releases the hammer, and hammer comes and hits the poison. Poison is released. Cat is dead because of the poison. Okay, but the question is, because of the radioactive material is in superposition of release and not release. Okay, which is putting the cat also in the superposition of dead and alive. Okay, so these are all interconnected. Okay, so even though at a macroscopical level, Schrodinger cat experiment, it's a Schrodinger, okay, cat experiment, or it is also called thought experiment, Schrodinger cat thought experiment. What it is telling is things becoming existing in superposition states. Okay, but the question is, this kind of a superposition state is only going to exist. Superposition is guaranteed only when things behave as per quantum physics laws. Okay, what are those laws? Number one, okay, that should show both particle and wave behavior. Okay, to have that, the particle should be very, very small, just like de Broglie wavelength giving, if the mass of the particle is small, the velocity is reasonable, then in that case, 10 to the power of minus 34 is in the numerator. The mass of the particle, let's say minus 31 kilogram, the velocity is 10 to the power of meter. 10 to the power. In that case, I will get a measurable 10 to the power of minus meter, which is the angstroms. Okay, angstrom. So this wavelengths are measurable. So we can see the wave nature. Wave nature is there. So these are all connected. The wave nature is there. So as per the wave, if you just take a wave nature, if you just, okay, divide the wave into parts, if I take absolute square of the wave, what I will get, a wave absolute, okay, absolute square of a wave, I'll get probabilities with which a given particle which is creating wave can exist in some locations. So this is the location which exists. Let's say this wave is due to an electron inside a box, so there is a chance that electron can exist with a larger probability in some locations, this location and this location. Okay, wherever the wave is hitting 0 point, so the electron is not present there. So I choose the superposition of electron to exist here and realize a qubit out of it. Okay, so the at a very tiny level I can realize a qubit. Okay, and To see such a qubit, to see such a quantum nature, the between our level, we are at the macroscopic level. We are move at the meters or the centimeters range, but this behavior is observed at the angstrom nanoscale. Okay, so there is a range difference. Okay, there is a range of difference, you see, between macroscopic to microscopic. Okay, you see, this is few meters or few centimeters, and this is few angstroms. Okay, what is the difference? Difference is about 10 to the power of 10 orders, 10 to the power of 10 orders. Okay, in that case only we are seeing the quantum behavior from here. So to see in that, like, this is ambiguity is there, na? Ambiguity. To have ambiguity, ambiguity means superposition existing in multiple states at a time. To see ambiguity at classical level, okay, or real world level, okay, to see ambiguity at one has to go to astronomical distance and look back towards the earth. Okay, so that is the example, the movie Interstellar. Okay, if you see Interstellar movie, the hero travels to space. He goes to through black hole. He wormhole, I think it's called wormhole. He enters to a location where he is able to see multiple possibilities of time. Okay, so he can see the multiple chances things can exist. So he could see the childhood of his daughter. Okay, he could see many possible things in superposition. So answer to your question, Srinivas ji, to see a quantum nature or quantum states at our classical level, what you have to do, you have to go to the astronomical distance and see the same thing, then you can see that. Okay, so the you please watch this movie, you would understand what is possible in our mythology. Okay, it is being already addressed, like say the same, like our god Sri Krishna exists at 10,000 places at a time in superposition. It is like, it is like he is with his lovers. There are 10,000 lovers for Sri Krishna. At a time, he is existing with all of them in superposition. Okay, right? So you please think in that context, you will understand. When it comes to our saints, in some they were in the samadhi state, they are actually exist in the death state as a life state together. So they stop the entire biological system to a standstill, such a way there is no energy required, no need to take a breath. Okay, so they go to a meditation state. In that way, they are doing it. Okay, right. So yes, and later there were Lalit ji was asking, it can probably consider as a ground state. Yeah, of course. Death state may be the ground state, but signs are not that. Until somebody opens samadhi and see, we don't know what is there inside. Okay, so some Japan, like some Buddha monks were found to be their entire body found to be intact. It appears to be the body is alive. They're still in that death state, but the entire body is just existing. There are news on that. Okay, right. So again, biophotons are there, right, sir? Or can they have an effect? Biophotons, there is nothing like a biophotons. The photons are by nature electromagnetic. So even there are, like say, For example, there is a, light flies are there, na? They emit a light. Okay, there are reasons where the flies emit a light. Okay, and they emit a light because of a chemical process called I think there is a protein, luciferin or something protein is there. Because of that protein breaking into parts, it emits some radiation, the light. So that is what the light is seen. So that is also electromagnetic wave coming out of a biological chemical process. Okay, maybe you are referring to that. So, and one more biological related electromagnetic is the fish eel. It generates from his body electricity by some means of batteries inside in the bat. I think some biological process only. But so there is nothing like a bio current or anything. It is all coming because of the chemical current. Okay, fine. Okay, so then get back to the here. So emerging topological qubits, we know just discussed. Okay, and there is active research is going on in this potential game changer. It could be because it is going to address all our existing error problems. Okay, and there is a question here by Satish. We are obeying the quantum phenomena because we are in the quantum world. No, let me correct your statement. We are existing in a classical world, a macroscopic world. And if I just take a small device, if you break it into part and part, okay, and then at that level, there is a quantum domain or a quantum realm exists. At that location, the quantum physics laws should be used to explain the things, because classical physics laws or Newtonian physics laws are not going to explain that properly. Okay, yeah, Raghu was pointed out that bioluminescence from the light flies, how the light comes. Okay, fine. So, what is the difference between classical and quantum? Okay, so classical is the macroscopic world, a large world, our world, and microscopic is a quantum world. What is microscopic? The particles exist at the size of atoms, at the size of molecules. Any entities are at the size of angstroms, and their weights are of 10 to the power of minus 30 kilogram. Like that. That is the quantum world. The classical world, we are talking about few centimeters. The least thing we can think is millimeters. But in quantum world, the least thing is 10 to the power of minus 12, minus 15. Okay, right? So that is the difference between classical to quantum. Classical world and Newtonian physics laws are useful to explain things. Newton's first law, second law, third law, and other laws, electromagnetics laws, thermodynamics, like heat laws, are used to explain the classical world dynamics. But when you go to a small atomic level, you need to have a quantum physics to explain. There is something called statistical physics are derived from quantum physics that is required to explain. Okay, right? Fine. So that is a difference. Is there any difference in superstition in class superposition? I think you mean superposition in classical in quantum. See, in classical, there is nothing superposition. I think in a classical superposition is, we see in the classical superposition is seen in the case of, let's say there is one charge Q1, it generates electric field around, okay. Let's say E1, which is 1 by 4 pi epsilon naught Q1 divided by R square. What is R square? Let's say at this point, which is distance of R1, okay, what is the electric field at that point? Okay, let's say I have one more charge Q2. This also generates its own electric field. That's a positive charge, and it will also generate at that same location with some electric field too, 1 by 4 pi epsilon naught Q2 by R square. Now, if I ask what is the overall electric field total, which is simply a superposition of Q1 and Q2. This is a classical superposition you can think of. It's a sum of electric fields, sum of magnetic fields. If I have one, like, okay, this is a classical way of saying if I have a positive clump of positive charge, let's say a battery, okay, positive, negative battery, or one more positive and negative battery, you put them together, it is going to generate a voltage, let's say voltage of, let's say, plus 5 negative 5 volt and positive 5 volt. So you are superposing, means adding, just simple adding. In the case of magnetic field, north south, south north, it is going to generate a large bar magnet with increased strength. Okay, that is a superposition in classical world. But when it comes to quantum world, see here, superposition is not giving any ambiguity. Remember, ambiguity means confusion. Okay, there is nothing like this or that. It is certainly this. But this is a classical superposition. Okay, right? And now quantum superposition. Quantum superposition. What is quantum superposition? Quantum superposition is if you just take a quantum coin, you toss a quantum coin. How do you toss a quantum coin? You take a quantum state starting in 0, you add a Hadamard gate on that, you will going to get a superposition of 0 and 1 with equal probability. This is a quantum coin. Okay, just like a tossing a coin. So literally, what is it? You take an electron, electron in the ground state. So there is outermost orbit available for the electron. What you do, send a pulse of photons, pi by 2 area pulse. Okay, what is it? It has a photons, equally spaced photons. Okay, 1 micrometer, 1 microsecond apart. Okay, so what happens is this will come and hit a one electron, photon pushes to the excited state. By the time electron comes down, one more photon comes and hits it. So literally resulting electron going back and forth between 0 and 1, just like a coin being tossed. This is equivalent to a coin being tossed, that is coin during the flight. Okay, the coin, if you just take a head and tail coin, is tossed, so it exists in a flight state. Okay, that is what I mean. So quantum superposition is going to be having ambiguity, confusion, means I am not certain whether it is this or that. Okay, I don't know that it is this or that. There is a confusion. Why there is a confusion? Because the system is like that. So best way to explain that is using probability. Probability is used to explain. Okay, that is the difference. Okay, I hope I answered that question. That is the difference between superposition in classical and quantum. Okay, fine. So there are no more questions. Let's get back. Good questions were asked. Okay, now I have emerging platforms. One more emerging platform is diamond envy centers. What is this diamond envy centers are? Let me explain. I think once for all you will understand. That is the best way to go for that envy centers. Okay, so as you can see, the envy centers here is actually made from diamond. Diamond is consisting of carbons arranged in a very, very interesting way. This is what shown carbon arrangement. Okay, one single lattice or the lattice cell consisting of this many diamonds were arranged in a tetra pack stage, tetra packing. Okay, now what people do is, okay, take two carbons, remove from the lattice, okay, cell. You remove it, you create a vacant space of carbon slots. If some, there is a auditorium, students were sat, okay, there are two locations, I deliberately remove two students and create a vacant space there. Okay, right? That is what two carbons were removed and there is a vacant space. Now I just put only one carbon inside the one vacant space. I leave the other carbon without being replaced by anything. It's left vacant. It is called a vacancy. Now what happens? Okay, let me use my notes. Okay, so initially, let's say the carbon, 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 they're well connected. Okay, now the moment I replace one carbon or I just remove one carbon, okay, I replace two carbons. Okay, so those, so two vacancies are created. In place of one vacancy, I put a nitrogen. Okay, in one place, I'll not put anything. I'll just remove, leave things as it is. So nitrogen coming up with some extra electron becomes a negative in charge. And this one, there is vacant space, becomes a positive in charge. So this is just like a negative charge and positive charge separated. It forms a dipole. Okay. This dipole, the this dipole, if you just take the energy band, energy band, or I would say not energy, or orbital structure, orbit structure, or energy structure, if you notice, it will have two level atomic system. Okay, 0 and 1. Simple. It can exist in two states. But the sensitivity of this one is so much. Okay, even a small electric field around can split the ground state into two orbits, two fine orbits, and again excited state to two fine orbits. Okay, right? So because of external magnetic field or electric field. Okay, right? So the dipole energy structure. Now, initially the electrons were there. Let's say those electrons go and sit somewhere, let's say here. Okay, let's sit somewhere here. Now, I was thinking the energy separation is, let's say, 10 joules energy separation. Okay, now the electrons were here. They have an option to go to this level. They have an option to go this level. They have an option to go this level. Okay, let's say the how much energy separation here is, let's say there is a mismatch. The mismatch is so much. Let's say there is 9 joules. This is 7 joules. Okay, right? Now, in presence of the external magnetic field, the electrons have a chance to talk to. The photon is having 9 joules and 7 joules, but they will never able to talk to the 10 joules electron because their energies, like electrons cannot talk to, because they don't have that much energy, that the possibility to jump to that particular level. So now, if I send a photon of 10 joules to a diamond NV center. Okay, photon, a light laser source is incident. Let's say it is of green color. So if I get back same green color, okay, what I mean is, Okay, what I mean is there is no external magnetic field. External magnetic field is not there because if the external magnetic field is not there means electrons were here, they absorb the green light, they excite it and come back and emit the same green light. Okay, now when I send the same green light, when external magnetic field is there, that time what happens, these electrons, they, okay, the electrons were here will attract only 9 joules, but electrons at the bottom, if you see, if the electrons are here, they can exactly jump to the external level. Let's say this external level here, they jump, and then while coming back they only come back and sit at the here. Okay, when they come back and sit that level means they take 10 joules, emit, let's say 8 joules. Okay, so the second case, the green light is coming in, they emit, let's say, a pink color. Okay, so some different color is emitted, which means we can simply straight away say there is an external magnetic field, electric field and magnetic field is present. Because of that, the splitting is happened. Because of the splitting, the electrons were moved into the split hyperfine levels. Those electrons were showing this kind of a behavior. They are not existing in the normal orbital structure, the orbits. They are existing in a fine orbits. So, if I prepare a small probe where I put a diamond at the tip. Okay, so this diamond NV center is so sensitive. If I just take, there is a tissue, it has its own magnetic field lines. So these field lines will induce hyperfine splitting. Now what I'll do, I'll send a laser with a green light. If the reflected light is pink or any other color, I would say the tissue is having some magnetic field. Okay, what kind of a magnetic field, depending on the color coming out, I can just calibrate the magnetic field generated by the tissue. In that way we can detect there is a cancer malignant is there inside a material, inside the tissue or not. So basically for cancer detection, this technique could be used because it can give much more accuracy. Okay, right? So this is a NV center based qubits or NV center based sensing people can use as an emerging platform. Okay, so like say application is sensing, small quantum computing you can do. Okay, and advantage is it can work at the room temperature. Beautiful. Okay, so it can work with the room temperature means I don't need any cooling. Okay, right, right, just a minute. Satvik, I'm in a class, I'll call back later. Okay, fine. So the next one is photonic based systems. These were already being explored but not in a greater scale. But what is this, a silicon based photonics and non-linear crystals are involved. What is this non-linear crystal is? The non-linear crystals are very interesting entities. Okay, so non-linear crystals. Okay, what there is, if I have a material, if I apply the electric field, okay, electric field is applied and it generates a polarization or a dipole moment. Okay, as per the electric field in general, but non-linear material generates the electric dipolarization a higher order. Okay, so non-linear manner, the response and okay, whatever response would be in a quadratic manner, it generates the electric field. Sorry, it generates the polarization. Okay, if I take such material, non-linear material, if I send the photons, let's say 100 joules photon, if I send, it just emits two photons of 50 joules. It's like chops down an apple into two pieces, two are okay. In this case, it's not half, two halves of the apple. It's not that. As if one large apple is coming, would send, you get two small apples. Okay. So this is nonlinear crystal. Okay. So the weight wise to small apples is equal to the large apple. Now, interestingly, the arrangement of apples is in such a way, if the top apple comes inverted, okay, top apple comes as inverted, and the bottom apple comes as a just upright. So they are like entangled. Okay. So entangled photons. Okay. The spin of you can have a spin or a polarization of a photon. So top photon has polarization, let's say vertical polarization, okay, up, and the bottom one will have like a vertical again, maybe downwards polarization. Okay, they are opposite polarized. So this is how nonlinear crystals are going to play, and using the nonlinear crystal, you can create an entanglement. So there is something called a beam splitters are created using non-linear crystals. Okay, so here I was showing you the photonic based systems is like this. Wherever there is information going and then distributing, this is a beam splitter for you. Okay, so there is a beam splitter, there is a beam splitter. Okay, I think this is a beam splitter again. Okay, there is a beam splitter, there is a beam splitter. So they all come and interact, and then at one point they go and hit the detectors. Okay, so based on what is being detected, we can do the computation. So this is photonic based quantum chip. Okay, so advantage here, very good network connectivity. You can just simply connect them with optical fiber, and the room temperature they can be possible. And some of the challenges which we face here is probabilistic operations and scalability. Okay, fine. Okay, let me go to the next slide. Okay, yeah. So research methodologies, what one has to study is quantum, used to study them is quantum many body theory, means there are many bodies or many qubits are interacting. How to study them is using a branch of physics in quantum physics called a quantum many body system or a many body theory. One has to use. Another one is called density functional theory. Density DFT, density functional theory would tell me what is the chance of certain bond could be created, what is the chance of certain electron to be emitted from a given set of combination of qubits or atoms. So that is what density functional theory. And machine learning for material discovery. So a better material we have to find for qubits. So which is the combination of, let's say, semiconductor based quantum dots. So what is the combination of semiconductors we should choose to have a better controllability in quantum dots. So for that, there are so many factors are involved. So we can't study in lab. So we can do the simulation using quantum machine learning. Okay, right? So when it comes to experimental techniques in the research methodology, spectroscopy people use, transparent measures, the light measurements people use, scanning microscopy they use, quantum device characterization they will use, like Hall effect, all those things they use. So these are the research methodologies one can think of. Okay. And computational tools like ab initio calculations, quantum Monte Carlo simulations, and material database and high throughput screening. Okay, these are like computational tools. We are not getting into the details. Just for reference, I had put here. Okay, so what impact this can have? What impact this can a quantum material study can have is technology companies like IBM, Google, and Microsoft are developing quantum processors, so they can have a better quantum processors. Intel and Samsung, they are depending on semiconductor-based approaches. Okay, IBM, Google, Microsoft are depending on transphone-based qubits. Rigetti IonQ, they are specialized with quantum computing companies. They are specialized based on something called what is this? Quantum annealing based qubits. Okay, right? So the research institutions which can be impacted or which will be impacting is national laboratories and universities, international collaborations, sharing knowledge across each of them. Okay, so with quantum research, we can have an impact on that. So economical impact is multi-billion-dollar industry. The quantum computing going to be in 2030 multi-billion industry. So that is a very good big impact. And job creation, there are new career paths are going to come up in quantum technologies as the many governments are pouring in money for the quantum research and the establishment of labs and infrastructure. Obviously, to maintain them, we need a workforce. Okay, so innovative spillovers would be benefits to other technology sectors. For example, medical and the communication sector is the existing the domains which are actually experiencing or taking the fruits from quantum computing. Okay, so some of the key challenges, if you just notice, decoherence, as you can see, error rates, scalability, and material defects. These are the challenges one has to address through study. And research opportunities, novel material discovery, and hybrid systems, like somebody was pointing out earlier. A combination of different hybrid qubits together can have a better scalability. Okay, quantum classical interface. Okay, hybrid neural network they call, okay, in quantum machine learning. So by doing it, we can have a better results. Okay, standardization, developing industry standards and benchmarks. Okay, because just have a computer which is sitting somewhere, we should have a computer which is accessible and purchasable for everybody. Okay, right? So again, what is future? In next 5 years, improved coherence times, we can expect demonstration of quantum advantage in specific applications. Okay, not only medical, many domains. Okay, development of modular quantum systems. Okay, modular quantum systems. In next 10 years, fault tolerant quantum computer, perfect quantum computers, integration with the classical computer infrastructure, commercial quantum applications. Okay, commercially we can have quantum computers and also application. Long term vision would be large scale quantum computers for complex problems, quantum internet and distributed quantum computing. Okay, so in that way many problems can be, whatever NP hard problems could be easily solved by then. Revolutionary applications in science and technology. Okay, so these are the future research directions. Okay, so just to conclude, what we did is in today's session, okay, let me save this. Okay, so what we did in today's session is we talked about why one has to study quantum materials, what are quantum materials which is being explored currently. Okay, and study of quantum materials started in 1980s to the current, what is the status. Okay, critical research areas being explored, we saw. Okay, existing when it comes to quantum computing, what are the hardware platforms which is being used, what is the future hardware platforms, research methodologies to study this quantum materials, what one has to do, and having the knowledge and the research, what we could impact, or what is the impact of that research on the existing industry and institutions and economy. Okay, and existing key challenges for the study. Okay, and future research directions in next 10 to 15 years. Okay, right? So that is what for today. Now let me give you one more thing. Okay, there is something I wanted to plan. I wanted to even discuss about semiconductor physics, which is required for understanding the superconductivity and so on, those things. So I've prepared my lecture hand notes, which is about how many pages? I don't remember, 46 page. Okay, so I will add as a appendix material. This discusses why insulator is an insulator, why a conductor is a conductor. In the case of insulator, how can I realize something called super semiconductor? In the semiconductor, there is something called intrinsic and extrinsic semiconductors. Intrinsic means naturally existing semiconductors. Extrinsic means I create from doping. When I dope, what happens? When I bring two different kinds of semiconductors, one is N type and P type, when I bring them together, it forms something called a PN junction that becomes a diode. We take two diodes put together, it becomes a transistor. Why diodes behave like this in forward bias? Why diode behaves differently in the reverse bias? Okay, so what is the main workhorses of diode? That is minority and majority carriers. So in the case of reverse bias, there is a saturation current. Okay, so after that saturation current, breakdown happens in the diode, means diode just burnt off. Those things are all discussed. And also the energy level of this superconductor semiconductor materials I wanted to discuss, that is also there. Okay, for example, N type material, what is a band structure? P type material, what is a band structure? What is the temperature influence on the potential barrier? Okay, right? All those things are actually put together for your reference. Okay, this is a part of QT-08 actually. So that entire thing I can't cover in just 2 hour session, but for reference I am putting you for this. So semiconductor manufacturing, this all this whatever semiconductor based qubits, they actually manufactured from a material called a direct band gap, indirect band gap semiconductors. So those things were also put in the hand notes. Okay. So there is a survey of how the chip manufacturing is actually grown from very start to the till existing VLSI and higher dimensional chips. Okay, so that is all there in the hand notes. So when it is quantum QT-08, I would be discussing these things in detail, as I would be needing some few lecture sessions, something like 5 to 6 lecture sessions for completing all these things. Okay, so as of now, let's only concentrate on this. Okay, fine. So I'll stop at this point. There was a question some time back. Somebody was asking, Jalakshmi ji was asking, hope you post this semiconductor material is in class. Yeah, I'll be posting this my other hand notes also. Okay, okay. Difference between superposition and entanglement in quantum. Okay. Okay, that's one question. Classical sound waves. Is there any difference in superposition in classical and quantum? I answered that question. Okay, the next question is classic sound waves. Yeah, sound waves are classical in nature. Okay, and difference between superposition and entanglement in quantum. Okay, so let me answer that question. So there are two different things, remember. Okay, superposition means the quantum state being existing in superposition. Okay, let's say I have two quantum states. Now two. Okay, Now I put them together. Means I take one atom, another atom, put them in a box. They interact, they are going to create a new quantum state. When they are creating a new quantum state, they are about to create, it is represented by tensor product. Okay. So tensor product is alpha A, alpha B, 0, 0. Alpha A, beta A, beta B, 0, 1. Alpha plus, okay. Next one, beta A, alpha B, 1, 0. Okay, plus beta A, beta B, 1, 1. This is what results in when I bring two atoms together or two qubits together. Now, I can't write alpha, all these things. I'll write a short notation. Alpha 0, 0, alpha 0, 1, alpha 1, 0, alpha 1, 1. This is the two qubits which were put together. They are still just in contact, but they are not interacted, which means I can separate them into two quantum mechanical bodies, separable even quantum mechanically. Quantum mechanically. Remember, that is very, very important. Now, when they start interacting, what happens? Somehow the probability amplitude of this mid two states are destroyed. So what is left is, let's say 0, 0 plus 1, 1 with probability amplitude becoming 1 by 2, 1 by 2. This is left. Okay. Evolution somehow evoluted into this form. Okay. Right. Fine. So if it is evolved into this form, it is called entangled state. And remember one thing here, this entangled state is also in superposition between 0, 0 and 1, 1. See here, now the moment it evolved, this time I have to write AB, the compound system. And remember, this compound system never equal to a separable state. Okay, which means quantum mechanically I can't separate this thing into two parts quantum mechanically, but physically I can separate atom A and atom B. This is very, very important. Quantum mechanically separable, physically separable, both are not same. The quantum mechanically separable is this, physically separable, this is physically separable but not quantum mechanically separable. Two entities, it's like once somebody got married, they become two, one entity, they shared the ideas, they know each other. Even when the husband is working somewhere, we still say husband and wife, they are one entity. That is what physical separation doesn't mean they're quantum mechanically separable. Okay, right? So now superposition exists both even in the entangled state. Okay, when I make a measurement on one system, it forces that system to fall into the one state. Okay, and it destroys the other probability amplitude of other state. In a way, it destroys the entire state and forces the other atom also to come to the same fate. So that is the one of the consequence of the entanglement. So to answer your question, difference between superposition and entanglement in quantum computing or quantum mechanics is, when I take a single atom, I'll have a superposition in it. There is no entanglement in it. When I take two atoms, let them evolve in a different manner, not any manner, a different manner, so that they entangle and evolve to entangle. So in that case, this is a state. In this state, I have a superposition between 0, 0 and 1. Now I can say both entanglement and superposition is there. Okay, right? So that is the answer to your question. Fine. Whose question is that? Murli ji. Thank you. Murli's question. Okay, so I would be uploading both of my notes to Canva. Okay, let me upload quickly, right? And even I upload my notes, save, right? Save as a PDF.
Sir,
Okay.
quiz also.
Yes, sir. Definitely, I'll do that. I'll do that. Yeah. So when is the quiz due, sir?
For tomorrow evening, we are starting, sir.
Tomorrow evening. Ah, okay. Which means I have to. How many questions I have to give, sir?
15, sir. You
15
have
questions.
one class on quantum communication, sir. No, quantum computing. You have one class. One class on two classes on quantum sensing, and one class on quantum materials. So four lectures you have. So maybe
Okay. Four
13, 14,
lectures.
15 questions.
Yeah, yeah. I'll do that, sir. I'll do that.
Right, sir. Thank you,
Okay.
sir. So it is
So
time to thank Ashwath sir. Most of the questions have been answered. And yeah, I am sure you have enjoyed the style of teaching, especially we all enjoy the handwritten notes that is written when somebody writes on the board and teaches, it is easy to follow. And most of you have followed all this material and you can use the content for your own notes, prepare your own notes. We look forward for Ashwath sir's textbook, which is coming on quantum computing and the slides will be shared. So be ready for the quiz, which will be start tomorrow at 4:30. No, 5 o'clock. 2:30 will be the class tomorrow. Please note the timing. 2:30 will be the class. It will go until 4:30 or depending on the speakers. And accordingly, the quiz we'll have the valedictory session. Tomorrow we'll conclude with this thing. Some of you, whoever wants to share the feedback, you can share. Some of the experts who have taught you will be there. So you can give feedback to them. And after that, we will conclude this program and you write the quiz 3. All those who clear quiz 3, all those who paid registration fee payment that has been completed, they will be receiving the certificates. We will send them by email. On the registered email, you will register the same. We will give the information about QT-02 also. You can register for it immediately. And I think in another 7-8 days, we will start the second module for QT-02, which will be not a revision or not a similar content, but it will be slightly different. But of course, it will be reinforcing what we have learned. Uh, Maybe the foundation will be strengthened. That's what you can take it, right? So hopefully you are all ready for the things. Today we were supposed to start the quiz, but we thought we will have materials also in the quiz. So you can take the exam. I think you will have enough time, 1.5 day or something you can take and complete the quiz. Most probably we will try to release your certificates on Monday. Monday afternoon or evening, we will try to release the certificates, right? So thank you so much, Ashwath sir, for your time. We will continue to listen to Ashwath sir in the next few courses also. So we will enjoy the teaching style and also the content. And of course, the quiz questions are also, of course, will be tough. So please prepare well and write the exam well. And please inform your friends next time, next course. There will not be much restrictions, but you will have to ensure that you are registered through AP State Council for Higher Education. That is the only restriction. So again, Anil sir has not joined today, but Anil sir will send the mail to all your institutions, universities, and please inform your friends, especially those who are from maths, physics, electronics, and computer science and electrical engineering. Some people from materials and uh, mechanical engineering also may be interested to join because there are a lot of applications are going on in these days. So I wish you all the best. So best wishes for the exam tomorrow. Please don't miss because Professor Anil Prabhakar from IIT Madras will be taking a session on quantum communications and also talking about quantum computing in general, right? And then hopefully we may also have Dr. L. Venkat Subramaniam, IBM from IBM to also share some of his thoughts. And then we'll have our valedictory session. You can share some of your experiences of how and what you learned, and we will conclude with that, right? So thank you so much for your time.
So I
And
have
please,
uploaded.
yes, sir.
Yeah,
Yes, sir.
I have uploaded to the everything to this canvas, sir. So
Yes, sir. So all
people
the
can.
lectures are there in Canvas material. Nivedita madam's lectures and Ashwath sir lectures are there. So kindly take it further. Please read and prepare well. Hopefully, you will enjoy the